Welcome to Upstack America's IT training programs. My name is Bob and I'm the IT training lead for Upstack America. Today's training is on data science and specifically on artificial intelligence and machine learning. Our trainer will take us through today's session is Paul DeBacker. Paul is a data scientist with outstanding work experience managing digital transformation projects on artificial intelligence and machine learning. He also holds extensive experience as a solution architect for robotics process automation, and also he has experience as a developer for robotics process automation. Paul holds a Master of Science in Artificial Intelligence and Machine Learning from the University of Texas in Austin. He also holds a first-class honors Bachelor of Technology degree from Anna University, Chennai. Thank you for watching and we hope you will enjoy the training.
Today we're gonna be having so we are on the completion of week 2 on our course, and this is session 2 on basics of statistics. So just to kind of recap what we learned yesterday. So yesterday's session we spoke about a little bit of the basics of statistics. We tried to understand what is statistics, what are the various important types of statistics. We saw the different types of data that we have, right? So, Kevin, could you just tell me one or few more topics or things that we discussed yesterday, just kind of a refresher before we start today?
Yeah, we discussed about qualitative data, the two types, nominal and ordinal. And then we talked about the quantitative data, the two types which were discrete and continuous. We also touched on the descriptive statistics and inferential statistics. We also looked at the 5 V's of big data.
So this is good. Yeah, right. Absolutely. Then we saw what are the various measures of central tendency we spoke about, right? We
Right.
understood what is the measure of central tendency, that most of the data in any distribution tends to be falling under the center part of the data. That's what the central tendency theorem is talking about. So in continuation to what we were discussing, so today we will move ahead with the further statistical concepts, right? So Kevin, do you take any sort of a running notes during the session, or any pointers that you take?
Say that again.
Do you take any notes or pointers during the session that we go through?
Yeah, I do take notes.
That's good. Yeah, that's a good practice. So even I do it when I attend any online sessions, because there are a lot of things that gets discussed, but later on it's tough for you to recollect. So if you take certain notes and then when you rerun the recording, you can have your own writing of this topic, what you understand, and re-listen to the video. It makes little easier. So that's a good practice, right? So in today's session, so yesterday we stopped at certain measures, right? So we said that we will be talking about, so we understood the concept of different descriptive statistics, where we understood what is the measure of central tendency and what is the measure of dispersion, right? So we saw that the measure of central tendency tells us that, if we plot our data at a let's say at a histogram level or at a bar graph level, right, then most majority percentage of the data tend to be at the center of my distribution. That's what is the measure of central tendency. And what does the dispersion says? The dispersion says that if I draw my data within a certain range, dispersion is the measure of how widely spreaded is my data. So if I have a dispersion which is something like this, I can say with respect to my mean, I can say my data is widely dispersed. And when I have a certain distribution like this with respect to my mean, I say that my data is closely dispersed. Like the spread is close here, the spread is higher here, right? So that's where we ended yesterday. So now we're going to talk about something called as measure of central tendency, right? So measure of central tendencies, how do we do it? So we understood that every data distribution that you take and you plot it against certain histogram or bar graph or something like this, your data distribution tend to fall at the center of your distribution. Now how do we know it? So there are various applications to it, so methods to it. The very first or the very basic thing that you can learn about is measure of central tendency is something called as mean. So what is mean? Or a statistical mean refers to the mean or the average that is used to derive the central tendency of the data. So we call it as nothing but mean or nothing but average. So if I give you the numbers like 2, 3, 9, 6, 7, and let's say 10, and I ask you to find the average or mean, what you want to do? You're going to add each of this, right? You're going to do 2 plus 3 plus 9 plus 6 plus 7 plus 10, and then divide it by how many? This is 3, this is 3, 6. So summation of each of these attributes divided by 6 is going to give you the average value of that specific numbers. And we find that as per central tendency, the average or the mean, if I see, will be somewhere here, right? So based on my value, though it is not in sequence, so if I put my numbers in sequence, I'll find a a mean value which will be somewhere in the middle of my range. So my class, this data distribution ranges from 2 to 9 at a scale, right? Maximum, sorry, 2 to 10. So if I sort these numbers, I'll get somewhere here. So this value, let's say, might be 2 to 10. It might be, let's say, somewhere around 4.5 or something, or 5.2, something like that. That could be the minimum average range of my number on a scale, right? So how do we calculate mean or average? So a mean is nothing, average is nothing but actually called as mean in the term of statistical measure. So if you want to create a mean, okay, in statistics or in Python, this is your mathematical formula. So we generally denote mean as mu in statistics. This symbol is called mu. So what we define as, we say mu is equal to, so now we saw that we will add all the numbers, right? So that's why we say this is the summation of I is equal to 1 to n x of I. So my I would start from 1 or any value, whatever is my range. So let's say I gave you certain numbers, 1, 1, 2, 3. Let's say I take till 20. I ask you to find the mean of 1 to 20. What will you do? You will add 1 plus 2 plus 3 plus 4 till 20 and divide it by 20, right? That's what is the formula here. So summation I will start from 1 is n will be equal to 20 xi. That means this will be broken into first 1, then 2, then 3, then 4, then 5. It will go till 20. Correct? Then I'll divide it by n. N is the number of data items that you have in the population. So, and you know these terms now, what is the population and what is the sample? We have already covered it yesterday. So I'll divide it by 20. So this will give me the average or the mean of the values from 1 to 20. So that's what is an average or a mean. So population mean is denoted by mu is equal to summation x of x divided by n. X is your data point values like 1, 2, 3, 4 till the range. N is the number of items that you have in your population. That means the length or the count of your population. And small n is in the number of samples. So now what happens is there are two ways. The concept is pretty simple, but there is something called as population mean and sample mean. So now let's say I have a data of customers. Okay, this is my population, for example. So I have customers who has bought certain amount of money, product from me. So let's say these are my customers in my population. I'm just plotting it in a mathematical space. Now I'm saying customer who has bought more than $300 value product from me. Like let's say you have bought $500 total amount of product from me. Bob has bought $200 of product from me. So I'm saying get all the customers from this population whose purchasing value is greater than $300. So that means I'll create a sample out of this population as per our yesterday's knowledge, right? This sample is representing customers who have bought more than $300 of total value, right? Now, if I want to calculate the mean of my entire sale amount, what I'll do, I'll denote it by mu, and I add all my value numbers, all the customers total sold amount divided by the number of customers that I have, that will give me the average or the mean value of my entire customer, that what is the mean amount of money I have sold. Now, if I only want to identify that for this sample that I created, where customers who have bought more than $300, I need to find the mean. The formula is same, but we denote the sample mean as X bar is equal to summation of X divided by N. N is the number of customers that you will have in your sample. So let's say in sample, I got 20 customers who have bought more than $300 from me. And I have, for these 20 customers, I have some value. Someone would have bought $301, someone would have bought $320, someone would have bought $410, like this. I'll have 20 values. So all these 20 values will be added, divided by the number of customer is equal to my X bar, which is nothing but the mean sample. Right? Clear, or any question? I think this is pretty simple. I'm just extending the explanation for a clear understanding. Any doubt in this?
No, that's clear.
Okay. So now let's move on to the next slide then. Now the concept of here is what we're going to talk about is nothing but median and mean. Okay, these are again the two important concepts when you talk about the measure of this a central tendency. So what is my median? Median is nothing but it is the middlemost observation when you arrange data in an ascending order of magnitude. Let's example smallest to greatest. So let's say I gave you numbers 5, 6, 10, 15, 20, 25. Now if you arrange these values in the order of their magnitude, that means 5 will come first, followed by 6, followed by 10, followed by 15, followed by 20, and then followed by 25. Now, what does median mean? Median is nothing but the middlemost observation in my data arrangement. That is 50% of observation would be above the median and 50% of the observation would be below the median. Okay. So let's say if I add one more number. So how many I have total? 3 and 3. So probably 15 would become my mean value, sorry, median value in this case. So what is the formula? I'll take number of data points plus 1 divided by actually the number of data points. Okay, so that's the general formula. So if I have, let's say how many data points that I have, so it says 1 2 3 4 5 6 7, right? So we can take n plus 1 divided by nth term. So if I take n is 7, so 7 plus 1 divided by, generally I think it's divided by 2 for getting the value of a mean, right? So if you divide it, you get the specific value, and that value becomes your median. So on that scale, 50, anything that comes, so when you create a median value, let's say these are your data points, you will see that if this is your let's say median, you have 50% of your value above the median scale, which we call, and 50% of the value which would be falling on the bottom side of the median scale. So that's your median calculation, right? And then the final one which we have is mode. What do you mean by mode? Value which occurs most often, that means maximum number of times. So let's say I give you a range of values called 340. Okay.
Paul,
Yes, please
I
tell
have
me.
a, I have a question about the median formula. You said n plus 1 divided by n, that will give you the median, or is it divided by 2?
Let me just check. I think it is n plus 1 divided by 2 ranked values. So if I take, let's say 2, 3, 4, 5, 6, and 7. So how many I have? It's 1, 2, 3, 4, 5, 6. So if I say 6 plus 1 divided by 2, which is 7 by 2, which is nothing but approximately 3.5, that's the median value. Let me just double check. Probably the image that I've put would be using a different concept, but I'll just double check for you. Yeah, actually it's n plus 1 divided by 2. That's the median formula.
Okay.
So if you divide it by 2, that's where you get the value. So it is like 3.5 would be my median value in this range of 2 to 7. So it's nth term. So n plus 1 divided by 2 is your median calculation formula. Okay. So in terms of your mode, right? So mode is nothing but the frequency of a value that occurs maximum number of times. So it's pretty easy to visually calculate when you talk about mode. And in Python, you don't have to know all these formulas. Okay, you don't need to know all these formulas in Python. In your NumPy, there are inbuilt packages, just one line. If you just type in that one line, it will tell you the entire mean, median, mode, and everything. But this is the theoretical part that we are learning. Then we will go into the hands-on later. Okay, but this is, I'm explaining you mathematically that this is how the formula happens. So what is mode? The most frequent value in my data set. So let's say if I give you a data set where you have values of 340, 300, 310, 340, 320, 340, okay, 350. Can you tell me what's the mode of these values?
Split 340.
Yes, absolutely, because 340 is occurring maximum number of times. So the frequency determines what's the mode of my value. So the calculation formula though looks little complex, you don't have to know it pretty much, because in Python we don't gonna use these formulas to write a code. We have our direct packages which will be helping me to calculate the mode, median, and everything. So generally what happens, if I plot a graph like this of my data distribution, okay, and let's say this is the mean. So here what I would be getting, right? So this is gonna be my, so my mode value always remains here, because here would be my highest occurrence. Okay, so my median might fall somewhere here. Okay, and this might be my mean. So this is how we have mean, median, and mode in mathematics. So if I quickly look into the formula though of mode, so it says L plus H of Fm minus F1 by twice of Fm minus F1 minus F2. So what are these? L stands for your lower boundary of the model class. So if I take these numbers again, so something like this, okay, 340. So H would take the size of your model, so it might be 6 or 7. Okay, then frequency Fm would indicate frequency corresponding to the model class. It's little complicated statistically if you want to calculate, so we don't want to get there, but yes, you can know the formula. Okay, and if you want, if we will see how do we calculate in Python. It's pretty easy, we don't have to know the backend formula though, right? So that was our mean, median, and mode. So now we quickly gonna see, so this was our measure of central tendency, 3 ways: mean, median, and mode, out of which generally we use in statistics or in machine learning, your mean and median is the values which is going to be used very much predominantly. We generally don't use mode that much, but yes, mean and median are the ones that we're going to use. Now sometimes remember this one line in median values are not affected by extreme values. What do I mean by this? So let's say I have a scale of a value ranging from 10 to, let's say, 3000. Okay, if I take a median of this value, then if I change the range of, if I change the extreme values, okay, now from 10, let's say if I cut down it to 100, and from 3000 I cut down it to, let's say, 2000, it can be either an increase or a decrease. Your median value will not be much affected. That's the property of a median, and I'll tell you, and we will learn why medians are used in certain cases, preferred over mean, because median are not biased or affected by extreme value. Now what do I mean? So if I tell you to take an average, I give you a numbers of 10 to 3000. Okay, if I ask you to calculate the mean, let's say you are calculating the mean, you are getting 2000 as the mean, for example, roughly, I mean hypothetically. Now if I change these values 100 and I make this as 400, 4,000, obviously your mean will change. 2,000 will never be your mean. So whenever your extreme values have a tendency to move either side in machine learning, and you calculate a mean, let's say we want to calculate a value of a specific attribute. Now what will you choose, mean or median? Now when you see that your extreme values have a tendency to deviate, never go with mean, because your mean will always change when your extreme values changes. When your extreme values might change, always prefer with median. Now you can make a note of this. We will see the implementation of it later, but it's a theory. Okay, so we go with always median because median is not much affected by the extreme values in your observation. It does not drastically change. So even though I have an attribute whose extreme top bottom values are changing, I still go with median so that my modeling, mathematical calculation of my model remains intact. Because if my model value changes in my attribute, my subsequent calculation would fail and my model will give me a different output. Okay, so moving ahead to the next slide, measure of dispersion. So measure of dispersion can be done with respect to certain types. So there were three types in my measure of central tendency: mean, median, and mode. And for measure of dispersion, we have range, we have interquartile range, something called as interquartile range, and then we have something called as variance and standard deviation. That is what we're going to see. The simplest of, easiest of all the measure of dispersion is nothing but range. What is the range? Range is the simplest of all. It is calculated between the difference between the maximum and minimum value. So if I give you a number set of, let's say 300, 300 and 350, 400, 450, blah, blah, blah. How will you calculate the range? You will take the maximum value, which is 500, okay? And you subtract it from the minimum value, which is 200, 300. So your range of this series is 200. As simple as that. So range is nothing but x maximum minus x minimum. This is one of the way to calculate your range, which is a kind of dispersion. Okay. Now the next thing is very, very important in statistics and also in machine learning, something called as interquartile range, and I have put two diagrams to it and I'll tell you why. So interquartile range is the measurement of difference between the third and the first quartiles. Mathematically, it is obtained when the first quartile is subtracted from the third quartile. So do you have any idea, Kevin, what is a quartile then?
Yeah, I think so. When you say the quartile, is that dividing into? Go ahead and explain. Maybe what I know is different from what.
No, but please go ahead. You can tell me. I mean, that's fine.
All right, the quartile range. It's divided. From what I recall, is when you divide it into 4 quarters, and you'll have
Absolutely.
the 25, the
Yes,
50,
yes,
75.
yes.
Okay.
Yes, you're right. You're right. So what is quartile? In statistics, a quartile describes a division of an observation into 4 defined intervals based on the values and how they compare to the entire set of observation. So let's say I have a data from 62, okay, 62, 63, 64, 64, 70, 72, 76, 77, 81 and 81. Now, when I calculate the median, what I'll do n plus 1 divided by 2. So my median will fall somewhere here. Okay. So my median value of this specific scale is 71. Now, your interquartile range says that your interquartile range calculation is nothing but the simplest formula of IQR is nothing but we calculate it as Q3 minus Q1. Now, what is my Q3 and my Q1? So beyond, when you calculate the median value, okay, when you calculate the median value, or if you see here in this diagram, it will explain you the Q3. So if I have my data, which is 12 to 17, quartile is nothing but when I divide my observation into 4 defined intervals. So if I have a data, anything, if I have to divide it in 4 equal intervals, maximum what I can do, each portion of my will be 25% each, correct? So 25% each into 4 is giving me 100% of my observation. So when you divide into 25, we take it as percentage. Okay, so 25% of my data falls here, 25% of my data falls here, 25% of my observation falls here, 25% of my observation falls here. So this entire scale is divided into 4 equal quartiles with 25% each. And we know IQR formula is equal to nothing but Q3 minus Q1. So how I calculate? So now in interquartile range, you have to identify what is your Q3 and what is your Q1. And if you subtract your Q3 quartile 3 value from your quartile 1 value, whatever is the output is your interquartile range. So for example, in this case, I see that this is my 25%, this is my bottom 25, top 25%. Now my 50% of my data is or observation lies here, 25% plus 25%, where I have my median value calculated as well. So my median is nothing but my Q2. Anything above my median is my Q3. Anything below my median is my Q1. So this is actually my Q2. Okay, this maximum or extreme value of the scale is my Q3. This minimum or lowest value of my scale is my Q1. So in this case range, they are saying that your interquartile range IQR, your extreme maximum value. That means when I am able to cover 50% of my data, which is in this range, it's starting from here and it's ending here, and this is my total 50%. So minimum value of my 50% is 30, which is my Q1, and maximum value of my 50% is 57, which is my Q3. So my IQR as per the formula is equal to, we know it's Q3 minus Q1. So that's what they've done. 53 minus 30 is equal to 27. So for this scale, your interquartile or IQR range is 27. So if you look into this diagram here, so in this scale, I have my median, which is here, right? And this is my interquartile range. So this is my 50% of my data falls here. Sorry, yeah, this line should be somewhat here. So this is my interquartile range. Here, right? So now when I see that this is my bottom 25 percentile, this is my top 25 percentile, and this is my and this here to here is my 50 percentile of the data observation. Now what is the lowest value of my observation if it is ending here? Q1 is 64. What is the maximum value of my observation if it is ending here? It is 77. So 77 minus 64, 13 is my interquartile value for this range. So that's how you calculate. So you divide into 4 equal intervals, and you have your Q2 there, which covers 50%. Minimum value of your Q2 is Q1, and maximum value of your Q2 is your Q3. Then Q3 minus Q1 is your interquartile range, right? And this is pretty much useful. So we don't have to do this by calculating and all those things. In Python, we have direct formulas to calculate interquartile. You can manually calculate, that's fine, but there are packages also which will help you to calculate interquartile ranges. So next is very, very important as per your machine learning or statistics, what is called as variance and standard deviation, right? Variance and standard deviation. So what do you mean by variance? I think we roughly discussed last time, yesterday's session. Variance is nothing but it is the expectation of the squared deviation of random variable from its mean, and it is informally measures how far a set of random numbers are spread out from their mean. So it tells me that variance is nothing but denoted by sigma square is nothing but summation of x is my extreme value minus mu is my mean to the whole square divided by n, which is my number of data points. So it tells me that if I take a random set of numbers from my population, how much is the spread out, how deviated or dispersed is my data or collection of random numbers that I've taken from my observation. So what is the data dispersion or the data spread out? So we don't calculate again, but this is a mathematical formula. We again do it directly in Python. So that's your variance. Now, what is your standard deviation? Now, standard deviation is the measure of average spread. That is, on an average, what is the difference between any data point and the center value of the variable? So, standard deviation is generally calculated, which is a complex formula. So, it actually tells summation of I is equal to 1 to n xi minus x bar whole square divided by n minus 1. So, xi are your observation values. X bar is nothing but is your sample mean, okay, divided by n minus 1. So we have again formulas. We don't have to know the formula or calculate it by heart. We will directly know how to calculate all this in Python. But standard deviation and variance are very, very, very important. So because we need it in we need it in our analysis, in our machine learning exercises. So standard deviation and variance are very, very important. Now we'll see something interesting here. So as I said, variance shows me on an average what is the difference of any data point, right? What is the difference of any data point from my and the central value of the variable. So what is the dispersion? So if you plot your data, which is something like this, okay, we always know that variance is sigma, and and your your variance square is what is my sigma square is my variance, right? Mu is my mean. So and standard deviation is given by this Sx, generally we call it as. So your data, when it is something like this, we will see there is a rule which we'll talk right after this. So we will come back to this diagram, but this is what is standard deviation and variance, and that's how it is calculated. Okay, important concept. Now, yes. So now, what is covariant of variation? What do you mean by covariant of coefficient of variation? Sorry. So coefficient of variation is defined as the ratio of standard deviation to its mean. That means
Well,
if I have my yes.
I have a question about the variance. Like, do you know what the accuracy of Python is? Does it go beyond 6 sigma? Like, does it go to like 99.9%?
Yes, yes, we will come to that. Yes.
Okay.
So 99.9% is calculated within your 3 sigma value. We will come to this. So that's what was the diagram which was which we were kind of looking here. So if you see here in Python generally, so when you have your standard deviation and variance calculated and you want to see your data spread, so the difference or the the rule is we go with mu plus minus 1 sigma with your mean and your standard deviation. Okay. Now, when you go with your mu plus minus 1 sigma difference, you are covering 68.2% of your data, which ranges from minus 1 sigma to plus 1 sigma. Okay. That's what we are doing here. When I go for mu plus minus 2 sigma, I cover 95.4% of my data. And when I go with mu plus minus 3 sigma value, I cover 99.7% of my data. Somewhere they say it covers 99.9 as well. So that's the spread of standard deviation. That's the dispersion. So we'll look into it, how much why it falls like this in after we talk about the coefficient of variation. So coefficient of variation is defined as the ratio of standard deviation to its mean. So if I have S as a standard deviation and X bar as the mean, so coefficient of variation CV is nothing by S divided by X bar. Or we call it as, if I denote my standard deviation as sigma and mean as mu, then I'll say my coefficient of variation is equal to sigma by mu. That's how we calculate it here. Okay. So what is the example that we can give? So let's say, what is the use of coefficient of variation, right? So let's say you have a So let's say you have three options. Okay, you have three options of three different stock and one bond. Now you want to know that which one would be actually effective for you with respect to your risk appetite. So if you buy stock A or stock B, or you want to go with any kind of a money bond C, which one will be effective for you with respect to minimum risk? So what you do, you will go and calculate the coefficient of variation. So let's say for stock A, your versatility or your standard deviation is 11%. Your maximum profit gain from this can be 15%. So if you apply, so which is nothing but this is my sigma, standard deviation or versatility, and this is my maximum, this is my profit gain that I can, get from this stock, which is my mu. So if you calculate this divided by this, your value is 0.73. Similarly, for stock B, you have a standard deviation or versatility of 16%, whereas your profit gain could be 19%. You have a value of coefficient of variation is 0.84. For bond C, you have a versatility or standard deviation of 6%, and your maximum profit gain, your profit gain could be 10%. You have a coefficient of variation called as 0.60. So here it is 0.73, 0.84, and 0.60. So if you have to decide that which one you would go, so you would definitely choose C, because coefficient of variation at zero point 0.6 would be having the lowest risk associated among these three. So this is actually kind of a coefficient of variation tells you the risk appetite, which would be kind of giving you the risk measure. So the value with the more less coefficient of variation you have with respect to any sort of your data observation, the less risk is associated with that. So if I take the standard deviation, versatility, and profit gain for each of these stocks, I see that C, which is not a stock but a bond, I have only coefficient of variation as 0.6, which is lowest among these three. So this would be the lowest in terms of the risk appetite I can think of. So I can choose bond C rather than buying stock A or buying stock B. So that means if I see into this diagram, so your coefficient of variation is nothing but the ratio of the standard deviation to the mean. That means if this line is the best fit line or the average or the mean line, and these green dots are my data point, your standard deviation tells that how far is my point lying with respect to my mean. That's the deviation, that's the coefficient of variation. So if you see, if I mark this as with the red dot, so if you see this dot which is pretty close to your let me clear this. So this dot which is pretty close to your best fit line or mean line, right? So this dot is pretty much close to your line, whereas this dot is little far. So it might have a bigger standard dispersion compared to this dot, because this is deviating little further from your best fit or your average line when you plot it graphically. So if these are your customer data points, okay, or any data points representing in a mathematical space, you can identify that which data points are deviating from your mean, that the range of dispersion or spread is more, and which data points are closer to your mean, that means their range or dispersion is pretty less. So that's called coefficient of variation. It is also one of the important aspect. So nothing but standard deviation divided by mean is my coefficient of variation. So we will see the utilizations of it when we do any sort of a machine learning exercise, right? Next, very, very important, normal distribution. And we will go back to that diagram after understanding what is a normal distribution. So generally when you take data distribution, okay, in mathematics, in terms of statistics, based on your various data types, there could be different types of data that you can differentiate it. We have something called as Bernoulli's distribution, uniform distribution, binomial distribution, normal distribution, Poisson distribution, exponential distribution. These are different types of data distribution to see the distribution or how my data is laid out. Among this, the important one that we're going to talk about is normal distribution, because that's what is the important one for us in any machine learning. So normal distribution is one of the important one. So normal distribution has another name. Remember this, you can make a note. So normal distribution is also called as Gaussian distribution. That's the another name. So you can make a note of it, that normal distribution, sometimes you might be hearing me, I'm explaining that the data is Gaussian, is falling under Gaussian distribution. So you have to understand that the data is the Gaussian distribution, nothing but it's the data is normally distributed. I'm talking about normal distribution. Sometimes the interviewer might give you a data and ask you, can you tell me what is the Gaussian spread of this data? That is nothing but they're asking, do you see that data is normally distributed or not, whether it's a normal spread, or how do you calculate the dispersion? That's what they mean. So normal distribution is also known as Gaussian distribution. Okay. So now any distribution can be called as the normal distribution when it has the following characteristics. Number one, the mean, the median, and the mode of the distribution coincide. Okay, we will see the graphs in the next slide. Let's see the theory part of it. When the mean and the median and the mode of the values coincide, the curve distribution is bell-shaped and symmetric about the line x is equal to mu. So what is bell-shaped? So whenever you draw a data distribution and your graph appears like this, we call this graph as bell-shaped curve. Remember this term? It is again. So if they ask you in interview, does your data follow a bell-shaped curve? That means don't confuse. You have to understand that they are asking whether your data is normally distributed or not. So when your data is normally distributed with any of these criteria, and then when you plot the graph for the data, your graph would appear something like this, because it's the measure of dispersion. Then when we have the mean, we will see what is the widespread of the data. My data might be, if this is like this, then it is, a wide close spread, and my normal distribution might happen like this also, where I can say the data is a widespread. So anytime when you see a graph which is like this, we call it as a bell-shaped curve. Okay. So first characteristics of a normal distribution is the mean, median, and the mode will be coinciding. The bell-shaped curve is the data distribution, which is also called as symmetric. We will learn about symmetric later. That's a different concept. But symmetric and bell-shaped where x is equal to mu. That means my mean is equal to this median value. Mean value here is my mu. Total area under the curve is 1. So always remember, whenever you draw any bell-shaped curve, okay, the total area inside this curve is always denoted has a fixed value called 1. Out of this total area under the curve, out of 1, we calculate various distributions, or we calculate various measures to understand how the data is distributed and like this. But anyways, when you have your data, ensure that your total area under the curve of the data is always 1. It's fixed. There is no deviation to it. Exactly half of the values are to the left of the center and other half are to the right. Now this is what is called as symmetric. Now what do you mean by the word symmetric? So symmetric is nothing but it has a equal spread at both the sides. So if I take this curve as a bell shaped, let me make it a little better. So let's say I am taking this graph as bell shaped, and if this is my mean, it is symmetric, means my each portion to the left and the right are equal with respect to my mean. That's when I call the graph is symmetric. Now when I create a graph, so let's say I have one graph which is like this, okay, and this is my mean. But next graph is something like this, okay, this is my mean. My next graph is something like this, this is my mean, okay. So now we will understand different types of symmetricity as well. So when my data is distributed like this with respect to my mean mu, this is my mean mu, this is my mean, and my dispersion mu is saying that the exact half value is representing left corner of my distribution and also the right corner of my distribution. That means my graph is symmetric with respect to my mean at both the left side and the right side. That means the area is equal here. So if my total area under the curve is 1, I have 50% denoted here and I have 50% denoted here. not more, not less. Equally divided is what is called as symmetric. If your graph is like this, then only you can say your data is normally distributed. Now if your graph appears like this, where your symmetricity is somewhere here but your mean is somewhere here, we call this as left skewed. We will talk about this later. We call this data is not normally distributed, but the skewness, there is a skewness. So when the data, when the graph is aligned towards a specific side, so it is aligned towards the right side, we call it is left skewed. We will see the definitions later. So here, with respect to my mean, my graph is not symmetric. It's not equal at both the sides. So I cannot say it is a normal distribution. Again, if my peak is at the right side, we call this as right skewed. Okay, with respect to my mean, again, it is not symmetric. So I cannot say that this is a normal distribution. So symmetricity is very important, that whenever I draw my graph, the equal half portion has to be on both the sides. So these are the certain characteristics. Then only I can say that my data is normally distributed. Okay. Now, what is the mathematical formula, which looks a pretty math heavy, but you don't have to by heart it, but just see how the formula is. So any function f of x, okay, to find the normal distribution, this is the formula. It's 1 by square root of 2 twice pi into sigma e to the power exponential of minus 1 by 2 x minus mu by sigma whole square, where my value of x can range from, this is what you should know by heart. That's an interview question, that what is the range of your value with when your data is normally distributed. You can say my x can range from minus infinity to plus infinity. You don't have to mug up this formula, but just see that the normal distribution mathematical formula is this is what is ingested in our Python packages, and when we draw graphs and everything, we can identify whether my data is normally distributed or not. Mathematically, if you want to compute, you have to go through this computation, but we don't have to do that. But this is the formula of my normal distribution, and my range of x in a normal distribution ranges from minus infinity to plus infinity. That means if I have a scale, this is my plus infinity range, this is my minus infinity range. So my data can be spreaded from here till here, right? Any questions on normal distribution, or is it clear?
That's clear.
All right, that's great. Okay. Now, that's the second part of it. How do we graphically talk about various normal distribution? Okay. So, the normal distribution, the mean and the variance of any random variable x, which is said to be normally distributed. Okay. How do we do it? So, we will say that let E of x is the mean, which is mu, and variance of x, that is where x is nothing but my sigma square, right? That's my variance, correct? So variance is nothing but sigma square, and square root of sigma square, which is nothing but sigma, is my standard deviation, right? So variance is sigma square, mu is my mean. Now, when mu is your mean and sigma is your standard deviation, if variance is my sigma square, then what is my standard deviation? My standard deviation is only sigma, right? So these are my parameters. Then if I want to graphically plot any random variable x, okay, I want to take any random variable x which belongs to category of natural numbers. Let's say n is the length of my x, like x starts from x1, x2, x3 till xn. Okay, how do I show it? I can say that if it is normally distributed, so the graph would something look like this. If I draw the mean, median, and mode, it would be something like this. So this is the blue dot is my mean value, the red dot is my again mean value, and if I have at a various standard deviation. Okay, so at a mean of 0.4 and standard deviation of 0.7, I have this. At a mean of 1.5 and standard deviation of 0.7, I have the red graph. At a mean of 0.4 and 1.5 standard deviation, I have the green graph. So that means you can see that whenever your standard deviation is more compared to 0.7, your standard deviation is 1.5, which is greater. You'll see your data dispersion is more here. So that's why the green graph here is widespread. But whereas when I take mean at a different value, but standard deviation same, that means my data dispersion is not that much. It's a closed dispersion and I don't find much difference with respect to my dispersion value. See, it is pretty much in line and I can say it is somewhat symmetric because my standard deviation was same. The moment I increase my standard deviation to 1.5, my data dispersion is increased and my graph has become widespread somewhat like this. Then in standard normal distribution, now there is something called as normal distribution, then mathematically or probabilistic distribution, mathematically when we say, we call it as standard normal distribution. It is defined as a distribution with mean 0 and standard deviation is 1. What do I mean by it? When I have my mean, that means mu is equal to 0 and standard deviation sigma is maximum value 1. In that case, I will say that my data is called as standard normal distribution. And what is the formula? It's f of x is equal to 1 by 2 square root of 2 pi e to the power minus x square by 2, where again my x should range from minus infinity to plus infinity. Okay, that's the range. My data range does not change, but the formula is little modified here because I have a mean which is 0. So if I go to my previous diagram where my this portion, this e to the power portion, okay, sorry, yeah, where I had my x minus mu by sigma, here my mu is 0 and sigma is 1, right? So this portion gets modified to my normal distribution and I have this one. So whenever I am saying that my data is standard normal distribution, always get that point. That means by this I mean that the mean of this data distribution would be 0 and the standard distribution of that data would be always 1. That's the definition of my standard normal distribution. And now when I plot a normal standard distribution, my graph is something like this. And you can see that if I have a mean which is nothing but here, this is my mean because 0 is the scale and my mu is equal to 0 here. Because I don't have any mean, my mean is 0 and my standard deviation is 1, right? So that means this graph, I can say this is this is symmetric on the right side with respect to my mean. Again, it is symmetric on the left side with respect to my mean. I can say my data is standard normal distribution where my mean mu is at 0 and my standard deviation sigma is 1. Right? So this is the definition of your standard normal distribution, very, very important in statistics and machine learning. So standard normal distribution, close eyes and think mean 0, which is x is equal to 0. Sorry, x is equal to mu and my standard deviation is 1. Right? So now let's look at the next thing which we wanted to discuss. With respect to my standard deviation and mean, okay, what are the things that we can learn further? So there is another important aspect in statistics called as empirical formula. Okay, so this is very, very important in stats. When we talk about empirical formulas, it's very important. So empirical formulas are nothing but it's a statistical rule that is defined by the statisticians globally. What does it say? It says the empirical rule states that for a normal distribution, that means I know what is a normal distribution now. So what do you mean by a normal distribution? A standard normal distribution means my sigma, my mu is equal to 0, my mean is 0, and my standard deviation sigma is equal to 1. That's what is a normal distribution, and my graph will always be symmetric. Sorry. My graph will always be symmetric. That means if I plot it somewhat like this, it will be symmetric with respect to my mean, where mu is equal to 0 and the data is bell shaped. These are the attributes that I understand when I say that it is a normal distribution. So what does the empirical rule states? It says that for a normal distribution of a continuous random variable. Now we know what is a continuous variable, what is a discrete variable, right? Nearly all the data will fall within the third standard deviation of the mean. Now what do you mean by that? So that's what was your question, right? Does it go till 6 sigma? It does not go till 6 sigma in stats. So as per the empirical rule, it says that if your data is normally distributed with mu is equal to 0, sigma is equal to 1, the data is bell shaped, your widespread, your dispersion of the data, majority of your data would have a maximum of 3 standard deviation. That means 3 sigma. So I can have plus minus, so that means that's what I said. So I can have mu plus minus of 3 sigma, which will cover my majority of the data. So empirical rule then divides the data into 3 parts. It says that whenever you go with the dispersion range of mu plus minus 1 sigma, you cover 68% of the data, which you see here. Mu plus minus 1 standard deviation. When you go mu plus minus 2 standard deviation, you cover 95% of the data. And when you go for mu plus minus 3 standard deviation, you cover 99.7% of your data range. And your total area under the curve is always 1, which is 100%. And your empirical formula divides or allows you to say that your normal distribution data of continuous random variable, your nearly all the data will fall under the third standard deviation of the mean. That means mu plus minus 1 sigma is 68% coverage of the data, mu plus minus 2 sigma is 95, and mu plus minus 3 sigma is my 99.7% third standard deviation of my mean, where I cover majority of my data gets covered with my maximum of 3 standard deviation. So that's the empirical formula, and that's how we plot it. So clear? Any question on this, Kevin, on the empirical formula side?
No, that's clear.
That's clear to you right now?
Yeah.
That's what you were asking. That was your question. That what's the dispersion, or what was the standard deviation to cover maximum 99% of my data? That's what you were asking, right?
No, I was asking if it's in Python, is it possible to go up to 6 sigma? But I understand the empirical rule covers to 99.7.
Yes, so there is no need to go till 6 sigma, right? Because why you have to go till 6 sigma? Because beyond 3 sigma standard deviation to your mean, you do not have any more data, because it's covering your 99.7% of your data points.
Some company I work for at GE, they hold their standard to 6 sigma. So when you're presenting the data, they wanted you to go up to 6.
Oh, they want the data to go till 6 sigma of standard deviation?
Yep.
Okay. Let me check that, because beyond 3 standard deviation, okay, I have to check this then. Probably that's a pointer for me as well, because I haven't explored beyond 3 sigma. So what do you generally do then? If they ask you to go till 6 sigma, what's your task? How do you do it?
We used to do it in a Minitab, where we presented our data at 99.9%.
But when you cross 3 sigma to your standard deviation, you already cover more than 99, right? So what is covered from your 4th, 5th until your 6 sigma? Remaining, what portion is covered? Like, how do you do it?
Say that again?
No, you are saying that you are going till 6 sigma of standard deviation to cover 99% of your data, right?
99.9.
99.9, okay.
Yeah.
Okay, that's for 6 sigma standard deviation.
Yeah.
Okay. So I think then in that case, if I'm not taken wrong, and with respect to my statistical knowledge, so if 99.7% is covered within my standard deviation of mu plus minus 3 sigma, and you are saying that you move ahead to mu plus minus standard deviation of 6 sigma. That means from here to here, I have only 0.3% of my data range to be covered, right?
Correct.
So the dispersion, so the dispersion or the spread that you see till 9 mu plus minus 3 sigma would be pretty more compared to when you see the dispersion at mu plus minus 6 sigma, because you have only 0.3% of data points left to be covered. So that's a good point. Then might be that's a very advanced version of statistics, yes, because what we are learning is pretty basic. Yes, I'll check that piece then. Yeah, that's a good thing.
Okay.
So but with respect to statistics rule and with respect to the machine learning expertise that we are going to learn, so we cover standard deviation to plus minus 3 sigma to go at the extreme of 99.7% of my data coverage. So what happens generally, that's what we do. So when we see that I have to go with the widespread of mu plus minus standard, mean deviation, like, one standard of my mean, I'll obviously know that this dispersion is covering only 68% of my data. That's quite obvious to me, not evident for me to understand. So here, if you see this graph, 50% this side, 50% this side, okay? So they have their extreme values, okay? So if I have, this is my mu, okay? This might be, so this is my mu, and with respect to this, they are saying that, okay, this is covering my 34% of the data, which is symmetric with respect to my mu. Then with respect to my mu plus 2 sigma, I'm covering more 13.5% towards both sides, and mu plus minus 3 sigma is covering 2.5% of the data. So if mu mean is at 0, I deviate till towards how much? I deviate here to mu plus minus of 2 sigma value, which covers, which gives me certain range in terms of your empirical rule. But when I go plus minus 3 sigma, I cover up 99.7% of my data. So if I kind of revert back a little, okay, if I kind of revert back a little to this diagram, what we were talking about, the standard deviation and dispersion variance calculation, right? So that's what we were trying to say here, that if you have a data range, if your mean is at mu is equal to 0 and your standard deviation is always 1, your mu of 1 sigma, your mu towards this is covering 68, 95, and mu plus minus 3 sigma is covering your 99.7% of your data points. So that's what was the standard deviation representation here. Now, very, very important, and that's the last topic in today's session. With this, we're going to conclude with this week's basics of statistics. 5-point summary is very, very important in your machine learning exercise. Okay. So if looking into the presentation, can you have any guess, Kevin, that what could be this 5-point summary telling me in machine learning? What could it be defining? Just a guess.
It could tell you about the distribution of your data. Because if they all coincide, if you look at your smallest and your largest, and then you look at where the median stands, you could tell if your data is normally distributed.
Absolutely. So 5-point summary, I'll show it to you in Python. It's just a one line which will tell you this entire calculation, what you have seen, all these formulas. It can be just done with a one liner. And it's just a word that you type in Python and you get this entire information of standard deviation, variance, all these huge formulas that you have seen, how it is pretty easy. So 5-point summary is a set of descriptive statistics that provides information about your data set. So when I give you any data, let's say sales data of Amazon of 1 year, any bank's data, customers credit risk data, or any data in statistics will have its own descriptive dispersion. So to know the dispersion of the data, or what is the data telling me about, It consists of 5 important sample percentiles. The first one is the minimum value, which is x smallest. Then the first quartile, which is nothing but in IQR we have learned called as Q1. The second one is the median value, which is the midway point. At least 50% of the data falls in median. We know that any median value, 50% at the bottom and 50% at the top. That's what is the median value. Okay, that is my Q2 actually. So when you plot your IQR range, so this is your range, this is your Q1, this is your Q2. Remember, your Q3 is nothing, Q2 is nothing but your median value, because it covers 50% this side, 50% this side. Okay, then you have the third quartile, which is denoted by Q3. So remember this calculation here. Your Q1 always covers 25 percentile or percentage of your first quartile. Okay, that's what it is telling. Your Q2, which is median, covers 50% of all the data, and your Q3, which is your quartile 3, covers 75% of the data in the third quartile. Okay, and then you have the x largest, which is the largest value in your data set. So this, any data that you are given, okay, any data that you are given in machine learning exercise, one of the common steps, just close your eyes and always do a 5-point summary, whatever data I give you. So that tells you what is the statistical analysis, or what is the quartile range, what is the dispersion of the data spread. So I'll just we'll just show a quick demo of this, what we are talking. So just give me a sec, let me pull up the Jupyter notebook here.
Paul, you might be on mute.
Oh yeah, I'm just pulling up the Python code notebook actually. Just give me a sec. We will take one of the previous exercises data frame that we created. Okay. So let's go back to one of our previous Python exercises in pandas, and let's see where we created the data frame. Yes. So here was the data frame that we created on various scores, right? So I had my teams, I had my columns ABC up to till J, and I had the various scores, and I had certain numerical values. So let's say each index denotes any team, okay? And these are their respective scores. So if I run this data frame, it might give me an error because I haven't imported, yes, because I did not import pandas here. So what I'm going to do here is I'm going to say go import pandas as PD and then run this cell. Okay. So it's executing. So your Jupyter notebooks are always pretty much volatile. So if you start a new session, your kernel forgets about everything that you ran previously. So you have to rerun things again. So I'm not importing the libraries. Okay, yes, now it's created. Okay, yeah. So if I print my data frame here, I see this. So as I said, it's just a one-liner. So now this is my data frame where I have all the values. Now if I want to see all these learnings that I have gone through, what is my standard deviation, what is my mean, okay, not the variance, not the coefficient of variation, but mean, interquartile range. See, three things that we need very common is your IQR, interquartile range, your Q1, Q2, your mean, that means Q2 will always obviously give you your median, your variance, and your standard deviation. So how do you do it in Python? So just take your data frame name dot, use something called as describe. It's an inbuilt method in Python. And the moment you run this cell, everything that you need, you have got it. So with respect to this data, just one method of describe, and it is self-explanatory. If that means I'm asking Python to mathematically describe me this data frame, see what it has done. It has calculated the count. That means each column has 10 values. It has given me the mean for each of the columns. So for score 1, okay, what is my mean value? It is my minus 0.36. For score 2, my mean value is minus 0.22. For score 3, my mean value is minus 0.162. For score 4, it is a positive mean. For score 5, it is 0.45. So it has given me column-wise mean value. It has given me standard deviation of each column. Okay, so it has given me the mean, it has given me the standard deviation, it has given me the minimum value, which is nothing but x smallest. Okay, it has given me the 25th percent quartile value, which is nothing but the first quartile q1. So these are the 25th percentile or q1 values for my each column. 50%, it has given me median, that means q2. 50% of the data falls within the median. This is the q2 values. 75% of the values of the quartile is nothing but my third quartile, and maximum value, which is nothing but my x largest, is here. So your 5-point summary needs three things: smallest, largest, and 3 quartile values. So you get smallest, largest, and 3 quartile values. Along with this, you get mean and your standard deviation. So if somebody asks you, giving a data, that can you tell me the 5-point summary analysis, take the data frame, say data frame dot describe, enter, done. Isn't it easy? So all these heavy formulas which you have seen here, this one and this one and this one, see the formula of standard deviation and see how easy it is to calculate. So Python has undergone this formula inside interior for me, and then it has given me the answer. So theoretically, I should know that this is the formula of standard deviation and this is the formula for variance. This is how heavy the formula of a normal distribution is. But when I present the 5-point summary, just a word for me to describe findings. So that is the power of Python. Any questions on this, Kevin?
No, that's clear.
So if I give you any data, let's say I am giving you a data which is having 3 million records. When you load it in Python, you will say, definitely you will load it from somewhere, right? You will say df is equal to pd dot something. You load it from Excel, you load it from database, wherever it is, you store your data in a variable called df or a data frame. Just do df dot describe with the open and close parenthesis. You get this information by Python. So maybe if your information is pretty heavy and size is high, Python might take some time to compute it for you, few more seconds extra, but this is the output you get. So next, from here, we will now see that, okay, once I have my standard deviation, I know my mean, I know my 5-point summary, how can I visualize my data? What do you mean by visualization? We will talk about the visualization from next week. So visualization is nothing but how do I represent this graphically? Or if I have to present my data, right? That's what we learned in statistics. It's collection, interpretation, analysis, and presentation. So visualization comes under presentation characteristics of statistics, which we will be talking next week. So we will see how to visualize all this in different types of graphs, what graphs are suited for what sort of data, how each graph is, giving us or helping us to analyze each characteristics of the data. Right? Okay, so I think, yeah, that's all for today's session. So any questions to whatever we have discussed today on today's topic?
Not at this time.
So are you pretty much, in line with the topics we have discussed? Maybe yes, you can, if you have taken some running notes, I'll encourage you to, go through it. And if you want to, revisit the session recordings, you can do it. And let me know in the next class if you have any queries. But, uh, I mean, today we have covered at least two sessions. So, how much do you think you have learned something new? What portion you were aware before, and what percentage you think you have learned new which you did not know before?
Well, this is familiar territory to me, statistics,
Uh-huh.
but
Okay.
the Python part is something new I've learned. The describe command, the one you just showed me right now, how to do it in
Oh
Python.
yes, this is a part of the Python, but that if you see, if the concept of understanding the theory which we took majority of the session today is just to see how things happen at a theoretical level. We do not may not be doing those extensive formulas as you saw. We never need them, but
Mhm.
we should know that theoretically this is what happens. If I don't know what is an IQR or how do I calculate an IQR, you might, interviewers generally try to see how good you are at the theory. So they might ask you what is the formula of IQR. They will not ask you what is the Python package that you use to calculate IQR. They will know that everybody knows the package name because they would have googled it or somewhere how to calculate IQR in Python, and then you know the package name or the process. You will, I give you the data, you calculate Q3 minus Q1, you get the IQR. But the concept behind it is what lacks. So they might want to see that do you actually know what is the formula of IQR? What is Q2 meaning? I give you Python describe gives you median. But if you don't know the theory, then you cannot say median is nothing but is your Q2, right?
All right. It's good to
20,
understand so you can know your outcome.
yes, 25 percentile of the data is nothing but my Q1. That's how you relate the theory with what Python describe is giving me. 75 percentage, it means I'm covering 75 percentage of my data using, which is my Q3. Then when I do a Q3 minus Q1 for each of these rows, I get each of the columns Q2 value, which is the median. Sorry, the IQR. I already have the median. Right? So if you are good at statistics and you know all the concepts already in hand, that's pretty good. And this is going to help us, when we move ahead with the future sessions, and when we really apply those concepts in different data, in different types of data to understand the machine learning expertise, it would be pretty easy for you to understand that.
All right.
Right? Okay, perfect. So I think we are good for the day. We'll catch up next week. Next week, we will be covering mostly the visualization part in statistics, which is actually, we will see how to do it in Python. The concept we will be using is all these mean, median, standard deviation, but the visualization is completely in the Python side. We will see some notebooks exercises. Mostly next week will be a little more hands-on because this week we have learned the theory. So we will see certain statistical exercises and how do we determine these empirical formulas in 75 percentile, 99 percentile, percentage, 68 percentage, and 95 percentage of the data. Okay.
Okay.
Right. Perfect. Thanks. You have a good day there ahead. Bye bye.
All right. Bye.